Alright, thanks for watching, and today I would like to show you how to diagonalize a 3x3 matrix, just to give you more examples. And especially I want to show you how to find the eigenvalues, because you usually are faced with cubic polynomials, which is hard to solve. So that said, the technique is the same as for a 2x2 matrix. And if you're curious, I have done a video on the 2x2 case. So let's calculate the determinant of lambda I minus a. So let's first find the eigenvalues. And by the way, some people like a minus lambda I, which is nice because you keep a and you just subtract lambdas from the diagonals. I like lambda I minus a because then you have an equation of the form, lambda minus something times lambda minus something. So you make less sign mistakes. So basically, take care of the sign mistakes first, and then you don't have to worry about them. So, and to do that, again, you do minus a. So like 1, minus 4, 0, 2, minus 3, 2, and minus 2, 4, minus 1. And on the diagonals, you just put lambda. So lambda plus 1, lambda, and lambda. And you might be tempted to do row reduction. Very bad idea. Instead, let's just use a cofactor expansion. So, zeros are your good friends. So let's do that here. And so then you get lambda plus 1 times determinant of lambda minus 3, lambda minus 1, 4, and 2. The minus minus, so plus 4 times the determinant of 2 minus 2, 2, lambda minus 1, and plus 0, but we don't really care because 0 is just 0. And then you expand that out, so lambda plus 1, lambda minus 3, lambda minus 1, minus 8, and then plus 4, 2 times lambda minus 1, minus 4. And then, you just expand it out again. So lambda plus 1, and then lambda squared minus 4 lambda plus 3 minus 5, and then, minus 8, plus 4 times, so 2 lambda minus 2 minus 4. And then you simplify that. Let me see, maybe here. So lambda plus 1 times, so lambda squared minus 4 lambda minus 5. And then plus 4 times 2 lambda minus 6. Is that true? No, so I already made a mistake. So 2 times lambda minus 1 plus 4. Okay, so 4 times lambda, 2 lambda plus 2. Okay, now I know that most commenters will say, hey, but it's so much easier just to factor out lambda plus 1 here and lambda plus 1 here. Yes, in this case it is true. But I want to show you a case that works in general, because in general you don't have those nice simplifications, okay? So in general what you would do is you would expand everything out. So you would get lambda cubed minus 4 lambda squared minus 5 lambda plus lambda squared minus 4 lambda minus 5 plus 8 lambda plus 8. And this simplifies to lambda cubed minus 3 lambda squared, and I think minus lambda and plus 3. Got it. Notice this is really, and the idea is we want to find the zeros of this. And also here, I guess you can also have a simplification, lambda minus 3, also here as well. Again, I understand in this example it might be easy, but I really want to show you a technique that's a bit more general. So blame the example for this if you like. Okay, now in general, how would you find the solutions to this? In general, it is a pain, okay? But there is a theorem called the rational roots theorem, which gives you sort of nice guesses for your solutions. And in fact, let me talk about that. So maybe second step. So our characteristic equation P lambda is lambda cubed minus 3 lambda squared minus lambda plus 3. And notice this first factor is 1. And what works here is that all the factors are integers, but in general you can do that. And we want to solve this equals 0. Now, there is this wonderful theorem, which I don't know how to prove. It's called the rational roots theorem. And that works really for, okay, it works and it doesn't work. It works for any polynomial with integer coefficients, provided that that polynomial has some, a fractional root, so a rational root. It could happen, I think, that it could not have a rational root under some cases, but usually in all the problems we give you, it's probably a rational root. So this actually kind of works. Now, what does the rational root theorem say? If this polynomial has a root lambda of the form a over b, so if it has a rational root, so if its root is a fraction, where a and b are integers, then it turns out a and b are kind of nice. So they're not 50,000 guesses for a and b. Namely, what we would have is that a must divide this constant term, so this term here, and b must divide the leading term. B divides here the leading term 1. And I always get confused about the order, but if you get confused about the order, think about the equation lambda squared minus 4 equals 0. Then, well, the roots are plus or minus 2. And you basically see the numerator has to divide minus 4, and the denominator has to divide 1. If it's b that divides minus 4 and a that divides 1, then it's weird. You would have roots of the form 1/2 or minus 1/2. So that's not good. So indeed, that is the correct thing. And look, there are not 50,000 choices for a and b. You basically have that a is plus or minus 3, because 3 is a prime number. If you had 4, it would be plus or minus 1, plus or minus 2, plus or minus 4. Okay. And for b, it's even easier. B is just plus or minus 1. And so, for your guesses, you just have to take all the possible combinations of fractions of plus or minus 3 and plus or minus 1. And in this case, it gives you 4 guesses. Okay. So it would give you lambda. So what possible fractions are there with, sorry, I forgot to say. Well, of course it's plus or minus 3, but also plus or minus 1. That's very important. Also 1 divides 3 and minus 1 divides 3. So, what possible guesses are there? Well, there's a guess with a is 1 and b is 1, so 1. And then the guess with a is 1, b is minus 1, so minus 1. And then same thing, so if a is 3 and b is 1, we get 3. And if a is 3 and b is minus 1, we get minus 3. And hopefully you should be convinced that those are really all the possible combinations. They're none other. And basically it'll always be like plus or minus some fraction of the two. So now those will give us our 4 guesses. And all we have to do is pray and hope that that one of our guesses works. In general, again, in the problems they usually give you, yes, one of the guesses will work, but it's possible that you're so unlucky that none of the guesses works, but that would just mean that the roots are crazy. So it wouldn't be doable for just a regular linear algebra problem. All right, so what you have to do, so guess, so plug in your guesses, so try out lambda equals 1. And let's see if p of 1 is 1. So p of 1 is 1 cubed, which is 1, minus 3 times 1 squared, which is minus 3, minus 1 plus 3. Let's see, dum dum, so dum 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 dum, and that's 0. Bingo! So in fact, lambda equals 1 works. Suppose this doesn't work. No problem. You would go to the next root and see what happens, and so on and so forth. And if none of them works, either the problem is too hard or you made a mistake. Either here, you made a mistake in this finding A and B. Okay, lambda equals 1 works, and I know some people will say, well, you can do lambda equals minus 1 and lambda 3 and lambda minus 3. If you get 3 roots, you are done. True here, but again, I want to show you the general case. So suppose lambda equals 1. What do? You would take this polynomial and then use long division. So, and notice we're still not at the eigenvectors, we're still at the eigenvalues. Oh my god, okay? So let's do long division. And let me show you amazing American long division. So, lambda cubed minus 3 lambda squared minus lambda plus 3. This we want to divide it by lambda minus 1. So we want to eliminate this lambda cubed. So let's multiply this by lambda squared. So lambda cubed minus, I think, lambda squared. If you subtract that from that, you get minus 2 lambda squared minus lambda plus 3. Now we want to get rid of this minus 2 lambda squared. So let's do minus 2 lambda, which gives you minus 2 lambda squared plus 2 lambda. And then we get minus lambda plus 3. Sorry, minus 3 lambda plus 3. Because we're subtracting this from this. And then let's multiply this by minus 3. And we get minus 3 lambda plus 3, which gives you 0. So indeed, another bingo here. And that works. And by the way, why do I say American long division? I don't know if you know the joke, but I used to know, well, I still know, but there is a French way of doing this, where you do lambda cubed minus 3 lambda squared minus lambda plus 3, and you divide it by lambda minus 1. The problem is, if you do it this way, the French way, you go down like that, and at some point, unless you plan it very efficiently, you just get stuck here and you continue your work here. But here, look at all this freedom that you have. So you have this whole whiteboard space to do this. That's why I think it's awesome American long division. And I heard that in Russia, I'm not sure if it's true or not, they do it this way. They do one way here and one way here. I don't know how that works, but apparently it's true. Okay, so what have we found? We found that actually our original polynomial, lambda cubed minus 3 lambda squared minus lambda plus 3 is actually just equal to lambda minus 1 times lambda squared minus 2 lambda minus 3. And this one you can factor out. So I know in America they're fantastic at factoring this out, but I'm not, so just think of it as lambda plus 1 times lambda minus 3. If you want, use a quadratic formula. And we want to set this equal to 0. So indeed you get that all your eigenvalues are 1, minus 1, and 3. which again you could have just guessed by using this rational roots theorem or by factoring this out earlier, but in this case it could happen that the roots are irrational, so this method would help us find those roots. Good, so those are the eigenvalues, and now we want to do the eigenvectors, but I will just do it briefly. Ain't nobody got time for that. So let's find the eigenspaces. So I'm just going to do it for one eigenvalue. So let's do it for lambda equals 1. And I would like to remind you that, lambda I minus A was just a matrix lambda plus 1, minus 4, 0, and then maybe just here, 2, lambda minus 3, 2, minus 2, 4, lambda minus 1. So that was your matrix. The matrix whose determinant you took to find the eigenvalues. Now all you need to do is plug in 1 for your eigenvalues. So a null space of 1i minus a, this case is just a null space of, so 2, 2, minus 2, minus 4, minus 2, 4, 0, 2, 1. Sorry, 0, 2, 0. Because again, to get the eigenvectors, for each eigenvalue, you find a corresponding null space. And to do that, you just row reduce your matrix. So simplify this first of all. So notice, for example, you can divide this by 2. You can divide this by minus 2. And you can divide this by 2. So this is the null space of 1, 1, minus 1. 2, 1, minus 2, and 0, 1, 0. And then you row reduce. So, for example, you multiply the first row by minus 2 and add it to the second row. So it's a null space of 1, 1, minus 1, 0, minus 1, and then minus 2. So 2 and then 0. Very good. And then 0, 1, 0. And then, I don't know how you want to do this, but you can, add 1 times the second row to the third row. So add them up. So null space of 1, 1, minus 1, 0, minus 1, 0, 0, 0, 0. And by the way, for those eigenspaces, at some point you should get a row of zeros, because otherwise it's not quite true. I think that's true. Yeah, okay. And then remember, so even though this is in row echelon form, for the null space, it's always best to get the reduced row echelon form. So make the pivots 1. So null space of 1, 1, minus 1, 0, 1, 0, 0, 0, 0, and just make this term 0. Okay, and then you get that this is the null space of 1, 0, minus 1, 0, 1, 0, 0, 0, 0. And then you would just have to solve for this. Remember, what is the null space? Is the set of solution of AX equals to 0, 0, 0. So if you do this matrix times XYZ equals 0, 0, 0, then you get X minus Z equals 0 and Y equals 0. Let me continue over there. And then what you get is simply, X equals Z and Y equals 0. And then you want to figure out X, which is XYZ. And well, X is Z, so Z, Y is 0, and we get Z, and we get Z 1, 0, 1. So the null space of, the eigenspace corresponding to 1, so 1i minus a, is just the span of 1, 0, 1. And just a couple of remarks, and one thing that I made this mistake at least 50 times when I took linear algebra, which sucks because there were just like 70 problems. So I made this almost every time. You should never, ever, ever, ever find that the null space is 0. If the null space is 0, it means you made an algebra mistake either in the row reduction or in finding the eigenvalues. Because the definition of an eigenvalue is a number such that this null space is not 0. Okay, and I don't quite remember the other remark, but yeah. And also, I guess maybe that was it. The null space is always the span of some vectors, and the point is this thing is what's called the basis for the eigenspace. So 1, 0, 1, this set is a basis for the eigenspace for lambda equals 1. So if you want to think of it intuitively, it's an eigenvector corresponding to lambda equals 1. And yeah, that was the first eigenvector. Now you have to do it for the other two, but again, I'm not going to do it right now. We have more exciting videos to make. So lambda equals -1, then you just get the span of 0, 1, 1, and lambda equals to 3, we just get the span of 1, -1, 1. All right, and lastly, so a question like this wouldn't be find the eigenvectors. A question would be really find an invertible matrix P and a diagonal matrix D such that A is PD P inverse. And to do that, D, it's simply your matrix of eigenvalues, which here is 1, 0, 0, 0, -1, 0, 0, 0, 3. And P is the matrix of corresponding eigenvectors, which here is 1, 0, 1, and then 0, 1, 1, and 1, -1, 1. So, in some sense, the order is important in the sense that, you know, for every eigenvalue, you have to give a corresponding eigenvector. But in the other sense, the order is not important because you can always switch the eigenvalues, provided that you also switch the eigenvectors. And if you're curious why this is true, there's another video I've done on diagonalization and Legend of Zelda, which is really cool and which you should watch. All right, we're finally done with this, and if you like that and you want to see more math, please make sure to subscribe to my channel. Thank you very much.